which is wrong. It doesn't turn out to be a parabola, it's something else. But I think the Bernoulli solved this one. I forget which one. But the solution's been known since the 17th century or something like that. It's been a while that we've known it. The math on this one is hard. But after a while, you find out it's like a cycloid. Ends up being the thing that you want. But I will tell you, the math in that derivation, it's tough. Now, next step up the chain is you can look at when your action is based on more than one dependent variable. Instead of just having y and y prime, we can have x and y and z and their time derivatives, let's say. And in this world, we tend to use dots for time derivatives. So this is like the time derivative of the velocity, of the y coordinate. And you can derive the Euler-Lagrange equations essentially the same way, but now instead of having just one Euler-Lagrange equation for your one dependent variable y and its derivative y prime, you get a Euler-Lagrange equation for each dependent variable, for each as many as you have, j equals 1, 2, da, da, da. You get n Euler-Lagrange equations, which will minimize this action, which is built from these n variables and their derivatives. Now, that allows us to do things like set up the free particle Lagrangian. So I'll talk more about this in the next class because I want to explain the physics of this. This is a way of reformulating classical mechanics. And it's really quite beautiful. It allows us to do things like set up the equations of motion for a particle sliding on a bowl or something like that. Or one of your homework problems is to find the equations of motion for a double pendulum. And it's actually pretty easy to do this with this setup once you understand it. So I'm going to try to really, we'll try to really work a medium level problem next class so you have a sense of something to bridge off of for your homework, I hope. This one's very simple. So the Lagrangian more generally is the kinetic energy minus the potential energy. So if you're looking at a free particle, the potential energy is just 0, so it's not present. So the Lagrangian is just the kinetic energy. Kinetic energy in Cartesian coordinates, in terms of the dot notation, is mv squared. But v squared is x dot squared plus y dot squared plus z dot squared, right? And so my Lagrangian is actually the kinetic energy in this case. And then you can set up the Euler-Lagrange equations. Partial k partial x is ddt of that. Partial k partial y is ddt of that. Partial k partial z, ddt of that. And what are those Euler-Lagrange equations? They are ma is equal to 0 in the x, y, and z coordinates. So we've derived the Newton equations from the Euler-Lagrange equations in this way. What's neat, though, is not that it solves Cartesian problems. What's neat is that it solves problems with respect to other coordinate systems just the same. Here's ds squared in, I think those might be, I got to be careful here. These notes are born of physics. I'm not sure which theta and which phi we're looking at. Got to remember, theta and phi get switched around in physics and engineering, just to make your life pleasant. Let's see here. So, okay, this is a giveaway right here. I'm using phi for a polar angle, for like polar coordinates here. So that would mean that the phi and theta are switched from their usual meaning. If you divide that by dt squared, that shows you the formula for velocity squared in spherical coordinates. It's r dot squared plus r squared sine squared theta, phi dot squared plus r squared theta dot squared in the physics theta phi. Yeah. What is it? Oh, yeah. If I could read my own notes. Thank you. I'm too close to the board, but thank you. Come on. This one's, so just, I wanted to give you one non-Cartesian example. So in, oh man, this is still not the way I want to think about it though. Curses. well, we got the whole next class to work on this stuff. I just wanted to get it started. Let me give you back your tests after I record the grade. You can hit it there. So yeah, you can turn it off.